Welcome to the Real Curriculum. The force F pulling a body of mass m horizontally at acceleration e on a horizontal ground. From Newton's second law of motion, that F is equal to the mass of that body times its horizontal acceleration, because the force and the acceleration are in the same direction, horizontal. As opposed to the situation where the same body of mass m is being pulled by a force F that is inclined to the horizontal at an angle theta and accelerating horizontally at the same acceleration e. In this case, because of the force is not in the same direction as the acceleration, then that F is not equal to me. Instead, it is a portion of ma, which is the force that is pulling this thing horizontally. Because of this body is moving at an acceleration that is horizontal, it means that some force that is not being shown there is pulling it horizontally, and that force is ma. But this force F is not equal to me, but instead it is a part of me. We call that component. It is a component of me. So it draws us to the main point of today. Component of vectors. So vectors are quantities that alongside their value, their magnitude, you have their direction also that plays an important role in their character. So examples of them are forces, moments, momentum, stress, weight, and a whole bunch of others. And something that is very useful in understanding components that we're going to talk about today is the vector diagram. A vector diagram is one of the peculiarities of vectors. Because of their direction, you can always show them diagrammatically with arrows showing their direction. So this arrow diagram works in a way that as far as the direction of a vector is being maintained, its position can be transformed to suit the nature of the figure that is going to be drawn, especially when you relate the vectors and the resultant of the vectors. For instance, you have a vector A and a vector B acting such. Because of the vector A acted like this and the vector B followed suit in this other direction, the flow like this, the resultant will be some vector that will act from here to here. Let's call it R. Also, when you have a vector that acts this way and you have a vector that acts this way, let's see X, let's call this Y. Let's maintain the Cartesian coordinates Y and X. Because of Y acts this way and X acts this way, their resultants can only be within this region, acting outwards. So to be able to close this shape to form something like this that you can work with, then you can transform the position of any of this or this so that it can become a closed figure, as I said earlier. So you could form something like this. You could transform this to this place, and this closes. You have Y, you have this shape. Or you can transform this here, and this closes. Then you have X. Whichever one you do is good. You don't need to do the two. But I'm just trying to show you that the transformation thing is something that is peculiar to vectors because of the directions and the arrow diagram that you can draw. So we know that when vectors act together, A, B, and you have their resultant arrow, and you form the closed figure by transforming the position of one of the vectors, maintaining its direction, something like this. You can always see that arrow is equal to A plus B. So you call arrow the resultant because it is the total of all the vectors that acted together. So A and B acting together results to arrow. Even if there are more than two of them, for instance, some vector v1, v2, v3, v4, v5, v5. There will always be room for the resultant to come in. Even if you have something like this, the resultant will always be the closing vector of this figure that would act in such a way from the beginning till the end of the flow of the directions of all the other vectors. So since all of them flowed like this, then this resultant will act like this. It will go against that flow to balance them, to be their results. So you can always write, let's call the resultant V. You can always write V equals to V1 plus V2 plus V3 plus V4 plus V5. Just as it did this. So you know what the resultant is. The resultant is a very common name when you talk about vectors, but the component is not so common as the resultant. But it's very simple. As the resultant is the one vector that gives you the total of all the other vectors that acted, all those other vectors are the components of the resultant. So A and B are components of R. V1, V2, V3, V4, and V5 are components of V. So anytime you have the resultant of a number of vectors, all those number of vectors are all components of that resultant. Simple. So now, using the arrows, you look at the ones that flowed, the ones whose directions flowed, then the one that went against that flow. The resultant will always go against the flow. So look at all these directions. This one went like this, then you see this one went against it. So these two didn't flow. So you look for the pair that flowed. So Q went like this, arrow went like this. So you see that Q and arrow flowed. Q is in this direction, then arrow is in this direction. So their direction flowed. Then P went against that flow because P is the resultant. So this thing is simply P equal to arrow plus Q. And the right answer here is A. So these are things that would most likely not be told to you in school. So like and hit the subscribe button, so I'll be encouraged to do more for you in particular. Thank you very much.